Hello, students. This video will give some explanation toward the periodic trend of atomic size. What you should be able to do is explain how the size of atoms changes as one proceeds down a group and across a period. And if given a selection of elements, you should be able to rank them from smallest to largest or largest to smallest. There are two things to consider when explaining the size of atoms. But first, how do we measure the size of an atom? Well, remember, we don't really have a set edge to the atom. We have a nucleus, and then where we find electrons is kind of fuzzy, right? We can just predict where they are. We can't know with absolute certainty. So even though we draw an atom as if it has a defined edge, it's kind of fuzzy. So how do we measure this? Well, what we can measure is where the nucleus is. We can definitely identify that the magnet that positive nucleus is. So for example, if we take an atom of lithium and bond it to another atom of lithium, now we definitely realize there's probably going to be a little overlap, maybe. All right, we can tell where this lithium nuclei is. So if we measure from nuclei to nuclei, it's approximately the diameter. But we usually cut it in half and then call this the radius. So again, as close as we can. But of course, when we talk about radius, we're talking about atomic size as we're comparing all radii. So usually, you'll see in your book that it talks about the trend being of atomic radius or atomic radii. Well, we get the idea of what we're talking about. All right. Now, when you are trying to explain why atoms change in size as they do, we need to talk about two things. One, the strength of the nucleus. Well, what gives the nucleus strength is the number of protons. And the greater the number of protons, the greater the strength of the nucleus. So for example, if we compare silicon with 14 protons to magnesium with 12, this is a stronger nucleus, a stronger magnet, if you will, in its pull for electrons, because there's more protons, there's more positive there. The strength of the nucleus is named a special term, nuclear strength, or nuclear charge. And for some reason, we symbolize it with a Z, with a little EFF. This is effective nuclear charge. So the kind of effective nuclear charge of silicon, we would say, is 14. And the effective nuclear charge of carbon, we would say, is 12. And so the effective nuclear charge of silicon is greater than the effective nuclear charge of magnesium. Okay, so as we proceed down a column, our nuclear charge, our nuclear strength increases. As we proceed across a period, it increases as well. Because atomic number increases, we have more protons and more protons. All right. So that's the first thing we need to look at. But the second thing is the position of especially the outermost electrons. The outermost electrons. Okay. So as we proceed down a column, if we just look at the alkali metals, we're putting electrons in the 2s, then the 3s, then the 4s, then the 5s. And remember, these coefficients mean energy level. So, for lithium, its furthermost electrons are in the second energy level, where for sodium, they're in the third. So if you go down a column, down a family, down a group, the electrons, the furthest, go to increased energy levels. So as we go downward, they're getting further and further and further away. But what about across the period? Well, if we just look at potassium over to krypton. Potassium, its last electrons, we are in the 1, 2, 3, 4th period, so that will be 4s1. Then we go to 4s2, then we go to 3d, and then 4p. So eventually, krypton, we are last putting electrons in the 4p. It would end with 4p6. Oops, sorry. All right. So you see, when we go down a group, the electrons are being placed at further and further and further energy levels. But as we go across the period, do you see, we're adding to different sublevels, but it's the same energy level. In fact, after the 4s, we go to the 3d. So, for potassium, if we say nucleus, and then the first energy level, second, third, fourth, okay, we're putting electrons here. Well, by the time we get to krypton, 1, 2, 3, 4, we're still putting electrons the same distance. Okay, so let's put this together. As we proceed down a family, our atoms get bigger. All right. Well, as we proceed down a family, effective nuclear charge increases. So our nucleus gets stronger and stronger and stronger in its pull for electrons. However, the distance of the electrons is also increasing. So even though the nucleus is getting stronger and stronger and stronger and stronger, the electrons are getting further and further and further and further. So that stronger nucleus can't really pull. And so the atom gets larger. Plus, we have all these layers of electrons in the way. It causes what we call shielding. That diminishes the pull that the nucleus can have for those electrons. So as we go down, atoms get larger. The nucleus is getting stronger, but the increased distance of the electrons negates the stronger nucleus. And plus we have shielding. There's more layers of electrons, which the nucleus is pulling for. So the actual strength that the nucleus has to pull for these outer electrons is diminished by the shielding. So, chlorine will be larger than fluorine, bromine is larger than chlorine, iodine is larger than bromine, and so on. So, if you're asked which is larger, barium or magnesium, it's barium because it's further down. What about gold versus copper? It's gold because it's further down. But what about as we go across a period? Well, I think we would definitely anticipate that our atoms get larger, but they don't. They get smaller. Potassium. It has 19 protons, 19 electrons, and those electrons are last in the 4s sublevel. Krypton. It has 36 protons, 36 electrons, and those electrons are last in the 4p. Okay. As we go across a period, effective nuclear charge increases. Whoa, this is a much more powerful nucleus than potassium. 36 protons compared to 19. So, krypton has a really powerful nucleus. But poor potassium, just 19. And its outermost electrons are in the 4th energy level. The same for krypton. Sorry, we're getting some overlap. But this more powerful nucleus pulls more strongly. We do have shielding, absolutely. We have shielding here. However, this is a much weaker nucleus than this is. So this will actually pull inward. So the first energy level is going to be a little closer. The second, maybe I should draw that in another color. The second, a little closer. The third, a little closer. And the fourth, a little closer. Where these guys, they're just not going to be held as tightly. Now, I didn't draw that to scale. if we actually take a look at a kind of rough kind of figure, if we see potassium compared to krypton, we can see what that more powerful nucleus does. In fact, as we go across the period, we can see what more protons do. In fact, one more proton can pull so much more strongly on the 4s electrons. And then look as we go through the P. So just one more proton, look the effect on the electrons that are being added essentially to the same energy level. So as we go down, we get larger, but as we go to the right, we get smaller.